Okay, write these 5 problems down and try to simplify them yourself. Pause the video and do that. Okay, so I know I squared, that is the square root of -1 squared, so that's -1. Now let me think, I to the third, I can write that as I squared times I. Well, I squared is -1 times the I, so that's -I. I to the fourth, let's see, if I write that out, that's 1, 2, 3, 4 i's. Here's an I squared and an I squared. So -1 times -1 is +1. You can do the same thing for I to the fifth. 1, 2, 3, 4, 5. I squared, or even better, since I to the fourth is 1, I to the fourth here is 1 times I. So then I to the sixth, 1, 2, 3, 4, 5, 6. I to the fourth is 1. Then I'm left with I squared, so that's -1. We're going to use those powers of I to simplify things like these over here. So take a minute. This is not in your packet, right on page 36. So let's recopy over our simplifications from the prior page. I squared was -1. I to the third is -I. I to the fourth was 1. And really, that I to the fourth, that's going to be our key one. We're going to keep going back to that. I to the fifth is I. I to the sixth was -1. So let's do I to the seventh. Since I to the fourth was our best, since that equals 1, that's going to be our go-to. So let's think, how many times does 4 go into 7? We can divide. That looks like a square root. It's not a square root, it's dividing. So 4 divided by 7, that's going to go in 1 time with 3 left over. So this is, the I to the fourth is that 1 time. So that's 1 times I to the third, because there's 3 remaining. Well, I to the third is -I, so our answer is -I. So let's do that with now 1 through 8 over here on the right. What we're gonna do every time is divide the exponent by 4 and see what we have remaining. So 4 into 29, 4 goes into 29 7 times with 1 remaining. So that means this is the same thing as I to the first. So then let's do number 2, which is I to the 47th. So 4 divided by 47, let's see, 4 times 11 is 44, with 3 left over. So that's the same as I to the third, but I to the third is not simplified all the way. Over here, we saw that I to the third simplified to -I. You can always think of it as I times I times I. This is I squared, which is our -1, and this remaining I left over. So pause the video here, try 3 through 8 yourself, and then unpause it to check your answers. So for number 3, 4 divides into 12 evenly, so that is just 1. For number 4, we're going to think about how many times does 4 go evenly into 82? Well, 4 times 20 is 80, and there's 2 left over, so this is the same as I squared, which is -1. For 5, 16 divides by 4 evenly, so that's 1. For 6, let's see, 33. Oh, 4 goes into 33. 4 times 8 is 32. So that means there's 1 left over, 1 I. 18, 4 goes into 18. Well, 4 times evenly, because 4 times 4 is 16. So that means there's 2 left over, which is -1. And then 43. Ooh, 43. 40 divides by 4, so that leaves us with 3 left over, so that's -I. Okay, so we're going to do these 3 more problems on page 26, so pause the video and write them down now. When we're reducing radicals with I, you must simplify the I part first. That's the first thing you have to do. So for example, in number 1, the square root of negative 2, I'm going to rewrite as I root 2. And then the square root of negative 5 is I root 5. So now when you multiply these together, I times I is I squared. Root 2 times root 5 is root 10. Well, I squared simplifies, that's negative 1 times root 10. So we're going to do the same thing with number 2. That's going to be I root 3 times I root 8. Not negative I root 3. Just I root 3. So now that's I squared times root 24. So negative root 24. If you want, you can simplify the square root of 24. That's 4 times 6. The square root of 4 is 2, so that's the 2 comes out and the 6 stays in. Now for adding, I can't add radicals together when the radicand, or what's underneath the radical here, are different. You can with multiplication combine them, but not with addition. So let's think, what is the square root of 9? Oh, that's 3. So this is 3i plus, and the square root of 100 is 10, so that's 10i because it's negative. So now I can add them together and get 13i. Okay, this is a page in your packet. We are going to make a diagram of how all the numbers relate to each other in the number system. So for some vocabulary, you can see here, they give us all the different kinds of numbers. So underneath this, I'm going to write out some examples for you. A complex number is any number in the form a plus bi. A complex number, every single number in the set of numbers is a complex number. That is our overall set. Then it's going to break down, we're going to get imaginary versus real numbers. So pure imaginary numbers, or imaginary, are things that are just bi. So things like 5i, 2i, the square root of negative 3, those are all imaginary numbers. Real numbers are all numbers that are not imaginary. So there's no real specifics that I can give you in real, except that now all these other kinds of numbers here, all of these other kinds are real numbers, and we're going to have specific examples of those. Okay, so in real numbers, we have rational and irrational numbers. Rational numbers are any number that can be written as a fraction of integers. So 1/2 is rational, 0.25 is rational, 0.3 repeating is rational. All those can be written as a fraction. Now, irrational are numbers that can't be written as a fraction. 2.7, 1828, it goes on and on and on. Pi, the square root of 2, those are all irrational numbers. Okay, so other real numbers are integers. Those are positive and negative whole numbers. So -6, +5, -3. We can even say I squared, since that's -1. We can say the square root of -16, since that's -4. So they're all integers. Whole numbers. So whole numbers are positive integers including 0. So 0, 1, 2, 3, and so on. And then last but not least are natural numbers. And those are whole numbers not including 0. So 1, 2, 3, and on up positive. So we're going to take all this vocabulary and we're going to put that into this diagram so that we see how all the different types of numbers relate to each other. So I started by saying complex numbers are the overall set every single number is considered a complex number. Within complex numbers, we have pure imaginary, and real numbers. Now, pure imaginary, we only had specific examples, whereas the real numbers, there's a lot of different kinds of real numbers. So now, within real numbers, let me make this bigger so I can get into those circles. Within real numbers, we had rational and irrational. So irrational numbers are over here by themselves, and rational numbers are here. And there are specific kinds of rational numbers, which is why we have these nested circles. We have these circles within each other. So the next step down is an integer, then whole numbers, and then natural numbers. So if we look at the big picture again, what this is saying, if I have the natural number 3, 3 is also a whole number, it's also an integer, it's also rational, and it's also real. It's not irrational, it's not pure imaginary, but it is complex. Let's take an irrational number like e. E is irrational, which means it's real, which means it's also complex. But e is none of these, and it's not pure imaginary. Let's do an integer like -5. -5 is rational. It's an integer, first off, which is rational, which is real, which is complex. But -5 is not a whole number, it's not natural, it's not irrational, and it's not pure imaginary. Let's do a rational one. Let's do 3/4. So 3/4 is a fraction of integers. So it's rational, but it's not an integer, it's not whole, it's not natural. It is real, and it is complex. So based on this diagram, you can see what types of numbers are considered more than one example in the number system. Okay, your homework is what's listed on your calendar. It's these pages in your packet, and you are done the video.